Okay, so especially those things on the back, if you want to hear me, you should probably come a bit forward. I will not be able to speak louder than this one. Okay, so any questions before we begin? If you remember last week, the last thing we were discussing was how a changing magnetic field creates an electric field. No, how a changing electric field creates a magnetic field. That was one thing we had discussed. And we had also discussed about the displacement current. And using the fact that changing electric field creates a magnetic field, we had also discussed how a single moving point charge creates a magnetic field around itself. To a first approximation, if you remember, if it is moving with a velocity v, it has a charge q. At a point r relative to the position of the charge, the magnetic field was given by q over 4 pi mu 0 over 4 pi times q v cross r hat over r squared. And basically, this was the last thing we had done. And we had also said that if this is the case, for example, we assume that there were two charges, each moving with some different velocities relative to each other. And then we had seen that the forces that they exert on each other, the magnetic forces that they exert on each other. Okay, so what is the direction of the magnetic field created by this charge? At the position of this charge, what's the direction? Well, you can just imagine this as a current carrying wire approximately. So just to right-hand rule, so it will go inside. What is the direction of the magnetic force acting on the lower charge? Remember, the force is equal to Q times E plus V cross B. B is inside, so V cross B is upward. Now, what about the magnetic field created by this charge at this point? Out of the screen, what is the direction of the force? V cross B is towards the right. Of course, we are assuming that Q is positive. So these are not action-reaction pairs as in the sense of the Newton's third law. So that was kind of one problem we had, because if you just imagine these particles, after some time, this will accelerate in this direction, so its velocity will change in that direction, which means it will gain a momentum in this direction, and this one will gain a momentum in that direction after some time. So the sum of the momenta gained by both of these will be in some weird direction, which will definitely not be zero. So apparently momentum is not conserved in this system. So we have to resolve this issue. So this is one thing we have to resolve over here. But before doing that, let's just review what the Maxwell's equations are. We had the Gauss law. We have the Gauss law for the magnetic field. Maxwell Ampere law. And the Faraday law. Now let's concentrate on these two. what are some of the predictions? Now, up to this point, we were always looking at some physical examples, starting from how the charges are moving around or how the currents are flowing. We were deriving certain conclusions. But let's just look at these equations without any physical motivation for the time being and see what are the possible electric and magnetic fields in a region if there is no charge or no current. If Q is equal to 0, I is equal to 0 everywhere, is it possible to have some electric and magnetic fields? It might be, I mean, if you just first think about it, it seems kind of weird that if you don't have any charge, what creates the electric and magnetic fields? How can they be there? But if you think of these two equations, especially these two terms, suppose somehow at some point you created a place where the electric and magnetic fields are non-zero. And then you remove all the charges. So what will happen to the electric field? It will try to go to 0, right? But if the electric field is, and also the magnetic field will be trying to go to 0. Both of them will go to 0. But if the electric field is going to 0, it creates a magnetic field. And if the magnetic field is going to 0, then it creates an electric field. So it might be possible that we have a configuration in which the electric and magnetic fields are, in a sense, self-sufficient, in the sense that each one creates the other one. So none of them go to 0. So let's first see if this is possible. And once we conclude that it is possible, then we will be discussing how we can create those. Now, I will just make a guess to start with. Let me assume that the electric field at the position or at the time t is given by, let's say, E0 cosine kx minus omega t, or kz times omega t in the x direction, and the b is equal to b0 cosine kz minus omega t in the y direction. I'm just making these up. Now, the next question I will be asking is it possible may I choose k, omega, E0 and B0 such that these electric and magnetic fields satisfy my Maxwell's equations? Because if that is the case, if I can show that these equations do satisfy these equations, then I have a prediction. And that is the Maxwell's equations predict the existence of electric and magnetic fields that behave like this. Now, first, let's look at what these mean. And so, okay, we wrote these mathematical functions, but what do they look like? How will they behave both in time and in position? These are what we will be calling the electromagnetic waves. So, and both of them are basically, the electric field, I'm assuming it to be in the x direction all the time. The magnetic field is always in the y direction. They are perpendicular to each other all the time. If these are the solutions, they will be always perpendicular. If you look at this function, cosine kz minus omega t, at a given time, and as a function of z, let's say t0, how will it look like? Just up and down, it's just a cosine. This is at a given time. So at this point, for example, this will be 0. At this point, it will be 0. At this point, it will be negative. At this point, it will be positive. Now, what is this point? How can I determine the z-coordinate of that point? What is 0? Z is equal to 0. So what is the coordinate? What is Z0?
Well, is it top point?
It's the top point.
You can derivate them.
So cosine has the maximum value of 1 when its argument is 0 or 2 pi or... Kz minus omega t, Kz0 minus omega t0 is 0, right? This is one of the maxima at least. Because if Kz0 minus omega t0 is 0, then this is cosine 0 is 1. Or it can be 2 pi, or it can be 4 pi, etc. Do you agree? So Z0 is equal to omega over k times T0. So what this basically means is that this is how this function looks like in space at a given time T0. I can just look at it at a later time. But at a later time, this Z0, if I increase T0, Z0 is also increasing. And the position of Z0, that is this maximum, is always at omega over k times T0, whatever the value of T0 is. So as a function of time, this shape will basically move in this direction. Do you agree? Well, if it is moving in this direction, what is the velocity? Omega over k. So whatever time t0 is, this function always has this shape. Its shape never changes, but the shape just translates. Well, as you increase t0, it just translates without changing its shape. And the speed of that translation is just given by omega over k, omega and k appearing over there. What is k? Well, let's see. You see, this function changes, repeats itself. It's always the same shape, repeated after the other one. And it's not repeating in time. You see, if the position of an object is changed in time, is just repeating itself, we call it a period. After one period, the motion just repeats itself. Here, the function repeats itself again, but also in position. If you displace it after a time that this point moves over here, after a displacement of this much, the function repeats itself. This is what we call the wavelength. Now, the cosine function repeats itself if you change its argument by 2 pi. So cosine k of z plus lambda minus omega t, this should be equal to cosine kz minus omega t. This is basically this statement that if you shift z by lambda, the shape doesn't change. But the cosine function repeats itself if the argument changes by 2 pi. So k times lambda should be equal to 2 pi, or k is equal to 2 pi over lambda. This is called the wave vector. Now, why it is a vector? You see, kz is nothing but k in the z direction scalar product with the r vector, the position vector. This is actually the wave vector. You don't have to take it in the z direction. You can take it in any direction, but it tells you what is the direction of the motion of your wave.
Is it in the 3D space?
Yes, this is in 3 dimensions. You see, if you look at over here, I'm writing the electric field at the point r, denoted by this vector r. It only depends on z. It doesn't depend on the x or the y coordinate, but it only depends on the z coordinate. I'm looking for such a system, such a solution. Whether it exists or not, we will see. But if we find it, it's basically, it will tell us that there should be electromagnetic waves. And if we can find a condition on omega and k, from that condition we can calculate the velocity of that wave. So that is basically what we will be aiming at. Are there electromagnetic waves? And if there are electromagnetic waves, what are their velocities? That is what we will be searching for. Other questions? Now let's consider what are the, for example, electric field lines corresponding to this electric field at a given time. Now, what is the direction of the electric field? The electric field. It's always in the x direction, wherever you go. So the electric field lines are, remember, the electric field lines are always tangent to the electric field vectors. So if the vectors are always pointing in the x direction, then a line that is tangent to these vectors that are always pointing in the x direction are, for example, let's say this is x, this is y, if this is z. Is this possible as an electric field line? Why not? No, there's no conductor. I'm just saying that I know the electric field. I'm given that this is the electric field. I would like to draw the electric field lines corresponding to this electric field. And the electric field is always in the x direction. So is it possible that the electric field lines corresponding to this electric field have such a shape? Why not? So, what's wrong with this one? Well, the tangent is pointing in that direction over here, if we have such a shape. But we said that the electric field is always in the x direction. So we cannot have such curves. The electric field line has to be the electric field line has to be perpendicular. This is not possible. So this is an example of an electric field line corresponding to that electric field. And we know that at a given time, the density of these electric field lines should correspond to the amplitude of the electric field vector itself. So for example, if this is our electric field, the cosine kz minus omega t, then the electric field lines look like this one. Nope, sorry. You see, the amplitude is large over here, large over here, large over here, large over here. So the density of the electric field line should be large at this point, at this point, at this point, etc. At these points, the electric field is 0, so the density of the electric field line should be very small. I'm just looking for, you see, what I'm looking at, I'm just looking at a region of space. Let's say, this classroom. I'm looking in this classroom. And I'm trying to find if it is possible to have an electric and magnetic fields that are described by these functions inside this classroom. Now, I don't know what these electric field lines do out of the classroom. So maybe they just go straight in this classroom, and when they go out, they terminate at a negative charge, maybe. Or when they go out of the classroom, they just close the circle from the top of the building. I don't know. The only thing I know is that the only thing I'm looking for is it possible to have such electric and magnetic fields in this volume? And in this volume, this is how the electric field lines look like. You see, they alternate their direction because the cosine term above is just positive, negative. So here it is pointing in the plus x direction. Here it is pointing in the minus x direction, plus x direction, minus x direction, etc. So that is why these field lines are alternating their directions.
So in this space, the electric field lines are coming from the right, from the fence,
I don't know. I don't know. I know that they are coming from outside this classroom and going to out of this classroom. I don't need to know what they do outside this classroom.
Which way is it going?
Which one? The motion. Well, we said that it is moving, you see, x. It is moving with this positive velocity. So this whole shape is moving in this direction. Up or down? Come. So here we have 3 bunches of electric field lines. Point up. So those are the directions of those electric field lines, and this is the direction of my electric field line. And the plus that direction is in that direction. Keep pointing up. And start walking over there. So this is how we are moving. Okay.
Sonsuza kadar mı yukarı gidiyorlar?
I don't know. They just go out. That's what I know. After going out of the ceiling, I don't know what they do. I don't really care. I don't need to know. Well, let's see. I mean, what I'm looking for is, what I want to prove first is that I can have such solutions in this classroom.
This is just a guess?
Just a guess. I'm making up. And then I'm trying to justify it. I'm just guessing that there might be such solutions. Well, why they are perpendicular? Well, if you remember all the examples that we had done about the induced electric fields and induced magnetic fields, they were always perpendicular to each other. So I'm just generalizing it. Let's just look at the electric and magnetic fields that are perpendicular to each other. And they are both moving with a given velocity. Let's see if it is possible. If it is possible, then that would be a prediction of our Maxwell's equations. So they should exist. If they don't exist, then there's something wrong in our equations. That is the next thing we will study. I mean, if they cannot exist, there's no point in looking for ways of creating them.
How was these things
As far as I know, which might not be correct, they were discovered more or less like this. That there were some solutions of Maxwell's equation that had these wave-like properties. So then the next question is, what are they? Do we observe them? Or how do we observe them? And that we will discuss after we study some of these properties. Now you see, I'm always saying that, okay, the light is an electromagnetic wave. How do we know? How could we conclude that it was the wave described by these Maxwell's equations?
I think it's kind of fun. I think it's kind of fun.
I also think it's fun. Well, let's see. Shall we continue? Yes. Yes, you. I mean, we don't know what their velocity are. I mean, maybe different waves have different velocities. I don't know. But I know that if I can determine a relation between omega and k, and even that relation need not exist, then I will know what the velocities are. I don't know. I mean, for the time being, the only thing I am assuming is, let's just look for such a wave. Does it exist according to our theory? Can it exist according to our theory? Then at the end, maybe we would conclude that k and omega can have arbitrary values independent of each other. Then we will say that, okay, we have these electromagnetic waves which can travel at various velocities. Or maybe omega and k are related in a particular form, should be related in a particular form. Then we will say, okay, it has this velocity. I mean, it will be just at the end of our analysis if we can show that such waves are possible. First, let's proceed. Now, does this help you visualizing what is going on over here? We have all these electric field lines, of course, in the x direction, pointing up or down. They're alternating, and they are all moving in one direction. Then we have the magnetic field lines in this direction here, in this direction over here. They're also moving with the same velocity, with the same electric field. And both as a function of position, you see, if you look at over here, as a function of position, they are changing their direction. So at this point, maybe the magnetic field is pointing in that direction. At this position, it is pointing in this direction. If you, as time goes on, the whole pattern is moving. Now at this point, the magnetic field is pointing in the opposite direction. So if you just look at this point, the magnetic field is pointing in this direction. At the next time, it is pointing in the opposite direction. So it's just oscillating back and forth at this point. Now, if I fix a point over here, at this point, the electric field is going up and down, pointing up at some instant, then it's pointing down at the next instant. The magnetic field is pointing in this direction at an instant, it's pointing in this direction at the next instant, etc. At this point. So if you average over time, of course, the electric and magnetic field will be zero, but only if you average over time. At a given instant, the electric field is non-zero, and the magnetic field is non-zero. Of course, assuming that you are not at one of these points. So are you able to visualize what's going on? Now, we will need that visualization in the next discussion. So if you are having problems visualizing, I can just invite our friends again and show it once more. This is the Z. Okay, this is the Z. axis. Well, the vertical line is this function only.
Diğer eksende de manyetik dalgalar.
This is x. Let me just plot the electric and magnetic fields together.
Bunlar bir bütünün iki parçası biraz.
Exactly. So this is x, this is y. In the x direction, I have the electric fields, and in the y direction, I have the magnetic field. So this is B. This is E. They are just crossed like this, and they're just moving. Yes.
But actually, nothing is going right? It is just alternating.
Well, I mean, in the sense of a matter moving to the right, the electric field is not a matter. So is something going towards the right? We will see in a moment. Which medium? We never talked about a medium when we were describing the Maxwell's equations.
But it is supposed to be moving.
What is motion? Anyway. Anyway, these questions I would like to leave towards the end.
According to one of Maxwell's equations, shouldn't the decreasing electric field increase magnetic field?
Now, the question is this one. We said that, okay, the electric field is created by a changing magnetic field. So if you look at over here, at this point, let's say, the magnetic field is not changing, so there shouldn't be an electric field, right? Well, it's kind of, there is a subtle point if you look at the equations. The changing magnetic field creates the integral of the electric field. If you just think of the integral as an antiderivative, well, okay, forget about those. I mean, maybe you are right. If you are right, we shouldn't be able to find a solution. Our assumption, this is our assumption. If you are right, then this assumption can never be correct. So we shouldn't be able to find such a solution. We will see.
But these things are that lines that, yani hocam bir yerden bir yere bir şeyin değiştiriyor ya sonuçta.
Changing what?
Yani ne bileyim, elektrik field yarattığı için başka bir yerde elektrik field'ın da yok olması, başka bir yerde başka bir elektrik field'ın oluşması gerekiyor.
Why?
Çünkü dengelemesi de yani.
Why? Why should it balance? What is balance? What do you mean by balancing?
İşte thermodynamic.
No, there's no thermodynamics here. Okay, let's continue. Now, first of all, if these are our solutions, they should satisfy the four Maxwell's equations. Just keep this shape in mind. Or let's see, these are the electric field lines. What is E dot ds? For these magnetic field lines within the volume that we are studying. Let's just imagine a closed surface, an arbitrary closed surface. What is E dot ds for this arbitrary closed surface? 0. Now we have these four Maxwell's equations. we are looking in a region where there are no charges. So if those are our solutions, this should be equal to 0 according to Maxwell's equations. Is it satisfied? Yes. So the first equation is satisfied. Let's look at the second one. B dot ds. I mean, these, just rotate these by 90 degrees and you get the magnetic field lines. So the integral of B dot ds is again 0. So the second Maxwell's equation is also satisfied. Now there are two left. E dot dl, this should be equal to minus d phi b by dt. This is one equation that we should satisfy. Now, of course, we should choose some surface to evaluate the flux. And the boundary, the edge of that surface is our loop over here. Let me choose a surface. This is my shape. Let me imagine this loop of height, let's say dx, and width dy, dz. What is the flux? This is, let's say, at the point z, at the time t. I mean, that point over here need not be the z equal to 0, so it's an arbitrary point z and at an arbitrary time t. What is the flux? Let me also take my guess. What is the area vector corresponding to that area? Dx, dz. In which direction? Just a right-hand rule. It's in the y direction. Flux, the magnetic flux, is just B dot dA. B only has the y component. Well, this is in the y direction anyway, so you just multiply the corresponding y components. This is equal to B0 cosine kz minus omega t times dx dy. What is the time derivative? B0 omega B0 sine kz minus omega t dx dy. From the cosine, I get a minus sign. From the time derivative of the inside, I get minus omega, minus minus cancel, so I have just omega. dx dz, you're right. No, this is the magnetic field lines. At this point, all the magnetic field is in that direction. Well, you see, as you go up, you are changing the x-coordinate. So what the magnetic field doesn't depend on the x-coordinate. So you have all these uniform magnetic field lines go all on this plate. There is a magnetic field line here, another one here, another one here, another one over there. They're all parallel and in that direction. They're all exactly the same. Because the magnetic field doesn't depend on x. So if you imagine all these lines, so there's a line over here, a line over here, a line over here, a line over here, a line over here. All these lines make a plane. Right? So that is why these waves are also called plane waves. Now let's continue. Any questions on how we obtain this flux? So we just have this area vector. Within this area, it's a very small area, so the magnetic field is more or less uniform. Since it's uniform, the flux is just the magnetic field times the area vector. And if we already have an assumption on the magnetic field at every point. We know what this area vector is. Just take their scalar product. So this is the magnetic flux passing through this loop. And here, this is the time derivative. So this is part of Faraday law. So we already know the right-hand side. Now let's come to the left-hand side. Now in that region, let me just plot it again. This is my ring. So let's say this is at the point Z, this is at the point Z plus dz. The electric field lines are upward. Let me just name the corners A, B, C, and D. E dot dl. This will be from A to B, E dot dl. From B to C, E dot dl. From C to D, E dot dl. And from D to A, E dot dl. Now, what is this integral from A to B? This is the direction of my loop. dl is pointing in that direction. The electric field is vertical. So E dot dl is 0. From A to B, it is 0. From C to D, this piece, well, this is the direction of dl, this is the direction of the electric field. They are perpendicular, so it's again 0. From B to C, from B to C, dl is in that direction. Now A to B is 0, C to D is 0. We have these two terms that are non-zero. Now from B to C, dl is pointing in that direction. The electric field is also pointing in that direction, in the same direction. Well, the electric field, since it only depends on z, it doesn't depend on x, it is uniform along this line. It is constant along this line. So I can just take it out of the integral. What remains is just the length of that segment. So this is equal to the electric field evaluated at z plus dz, because that is the z coordinate of that line, times dx. Now, if you go from D to C, this is the direction of dl. This is still the direction of the electric field. So when you take their scalar product, you get a minus sign, minus E of z times dx. No? You see what we did? From B to C, the electric field is upward. It is uniform. So I can just take the E out. What remains is the integral of dl, but that is just the length of that segment, the integral, and the length is dx. That's how we define this segment, dx. And the electric field is the electric field at the z coordinate, z plus dz, at the time t also. And similarly, I do the same thing for this other side. dl is downward, electric field is again upward. Now they are pointing in opposite directions, so that is why I have this minus sign. But on that segment, the electric field is the electric field at the point at the coordinate z. It doesn't depend on x and y. I'm just ignoring this t. I mean, just keep in mind that electric and magnetic fields, they all depend on time t. And times the length of that segment is again dx. This is equal to Ez plus dz minus Ez divided by dz multiplied by dx dz. That is nothing but the derivative of the electric field. And let's see what was our electric field. This is our electric field. So E dot dl, this is equal to dE by dz times dx times dz. Well, just using the expression for the electric field, we have minus E0 k cosine kz minus omega t dx dz. Sine, yes. Now we also have this result. But we know the Ampere's law. No, the Faraday law. E dot dl should be equal to minus d phi b by dt. E dot dl is minus E0 k sine kz minus omega t dx dz. This should be equal to minus omega b0 sine kz minus omega t dx dz. True, but I have a minus sign in the Faraday law. Okay, sine dx dz, they just cancel. And we have E0 k is equal to omega b0. Now what we did, we had assumed some solutions. We don't know whether they are solutions or not. But that solution, that assumption had some parameters in it. The parameters were E0, B0, omega, and K. They were all parameters of our solution. And we know that if they are the solutions of all four Maxwell's equations, at least all three Maxwell's equations, they have to those parameters have to satisfy this relationship. This is one constraint we have, one condition we have on our parameters. If this is satisfied, then Faraday's law is automatically satisfied. So this is now satisfied. To show that there are possible solutions of the Maxwell's equations, there's just one equation left. We have to show that our electric and magnetic fields also satisfy the Ampere's law in the form B dot ds, now B dot dl, it should be equal to mu 0 epsilon 0 d phi e by dt. So we should show that this is also satisfied for our proposed solution. Yes, and that we will do next hour. So what we had done, just to review. We just made this assumption. We don't know whether this is a solution or not yet. But we are just making an assumption that maybe we can have such a solution of the Maxwell's equation. Now, these equations already satisfy the Gauss laws. Two of the Maxwell's equations, they are trivially satisfied because the electric and magnetic field lines, they are just straight lines. they satisfy the Gauss law. This is non-trivial to satisfy, and we had seen that if this equation is satisfied, to be satisfied for such a loop at least, if it is to be satisfied for that loop, then the parameters in our solutions, proposed solution, has to satisfy this condition. Or this condition, we can also write it as E0 over B0 should be equal to omega over k, which was the speed of the wave. So E0 and B0, they are related to, they have to be related to each other. They cannot be just arbitrary parameters. And then there's still one more equation that should be satisfied, this one, the last one. And we will see that this will give us another condition. But that we will continue on the next hour. Now, any questions before you go? Which one? This one. Should I go up? Plane waves. It's just a name. It's the magnetic field lines, they are straight lines. And in this plane, perpendicular to their propagation motion, they are uniform. But if you just have many lines, it's just a plane. They all have the same amplitude on that plane. Okay, you can go for a break.